So it's 101 and I'm making fractals and I want to find a way to get some really good feedback going. So it's filming and broadcasting and filming itself and nesting the pattern in itself. And for example, I think that if I get a big enough object and I can host that over the original screen, I might get what I'm looking for. So I'm just trying to get a little sub window up, but the two programs are interacting and they're not letting me render what I want to render. I just want to get something on top of my desktop. I want to get something over this screen. So if it's big enough, if I move it around, I can cause some better feedback. I just need the right application that will open on top of it. Here we go. But the program won't let me do it. I want to open and minimize. Oh, it's frustrating. It's so annoying. I just want to get it through. Oh, here we go. If I resize this. Okay, there we go. And now I'll open up. No. And now if I open up this should sit on top of this. But every time it sits on it, it disappears. Like it's there. I guess it's there, but I can't see it. Sort of. Like I thought that my PDF would open and be on top of it. Maybe it's here, but I can't see it because it's disappearing. So it's actually here, but the computer won't render it. So if I left click, maybe I can grab it because I can't see it. I'm assuming it's here somewhere. Like, if that makes any sense. Okay, so we'll park that there. No, we'll resize it so it doesn't go to full screen. But there's a bug in the software. It won't let me resize it. So there's got to be a bug. And then if I take this over it, no, it's going behind it. So I am moving around my PDF, but it won't let me superimpose it over it for some reason. So not a good attempt at audio-visual fractals. Because look how many fractals I have. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Let me count it here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. It looks like 12. And for some reason 12 is an interesting number for fractals, because however they get scaled down, 12, like for example with paper folding and how paper thickness exists, 12 is kind of the limit of what you can make. And when you look at the dragon fractal, 12 is the most you can almost resolve when looking at it. And in the universe, they say there's like 11 dimensions in string theory. So I think and the universe must be fractal across some kind of time invariance. So I think that in fractals, the 11th or 12th dimension is important for its resolution. If that makes any sense at all. But you got to know the dragon fractal. Let's go to the dragon fractal. This could be fun. Usually it helps to be thinking really lateral to connect these dots in abstract mathematics and physics to come up with some idea on how everything is connected. And at this point in time, I'm struggling to get where I want to get. So maybe it's YouTube we want, or do we want Wiki? Let's go to Wiki. So okay, images, and we'll just do dragon fractal, and maybe you'll see it. and then you'll get what I mean about the resolution at the 11th dimension. Dragon fractal. Oh, here we go. So I think the screenshot is captured. If I move this around, you can see the dragon fractal. It's just an iteration. And if I go to large, no, we want to make that smaller. Yeah, well, you can see the dragon fractal, and if you count how many, like there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You can see almost like 11 kind of vertexes. And string theory. Let's look at string theory. Is it 11 dimensions that string theory is? And in topology and string theory, there's a connection with knots and the strings that Edward Witten has found. And one day I'm going to do a video and I'm going to explain just these little connections that I think are loosely linked. But it won't be anything really groundbreaking. It'll just be something to think about. String. And I found it amazing with chaos theory when you look at the Sierpinski triangle and how that gets created in numerous ways with chaotic processes with bifurcations and feedback. So we got to look at oh, we don't want to be here. We want to be on Google Images. I want to show you a, there we go. We can just leave this open on the desktop and then maybe they'll run side by side. So I can talk nonsense and you can see a bit of both. So what are we talking about again? We're talking about the chaos game. No, we're talking about how the Sierpinski triangle comes from two processes. The chaos game, which is just making a triangle and rolling a dice and putting a point halfway between the last corner and one end, and you know there's 6 sides of dice, but there's 3 conditions, so you got to pair them up so opposite sides of the dice are the same, 1, 2, or 3. And so with cellular automata, let me look up cellular automata. You get the same pattern. So in chaos theory, this is what's called a strange attractor, and strange attractors are creating stable patterns that come out of the chaos, and that is loosely, that has a connection to fractals, which is kind of hard to explain because I haven't formulated my ideas on that yet really good. Look, here's the rule 90. So it starts at the top and it goes down the way, and it makes a really nice pattern, and you get the same pattern from the chaos game. Now let's look at the chaos game. Let me see if we can get chaos game. Chaos game. Come on, YouTube, hurry up! Give up my brain. We're boring our YouTube viewers. I can't get the sidebar. Okay, here's the sidebar, so I can scroll down. Oh, here we go. Chaos game. No, it's this video here. Chaos game 148. God, it only has 930. It only has 938 views or something. It's this guy here. He's really funny. He's such a dork. Well, so am I sometimes. So he just explains how he makes the chaos game and how the chaos game makes the...
I'm going to show you how to play the chaos game. It's very simple to play, but it has
Michael, we love you.
Outcome. I begin with a big sheet of paper with 3 large points marked on it, labeled 1 and 2, 3 and 4, 5 and 6. Now what I do is I choose a point at random on the sheet of paper.
Okay, yeah.
Shut my eyes
so you make
that,
point 1. Also, you make a 3. So if it's 5 and 6, 3 and 4, 1 and 2.
What I do is I roll the die, and it comes up with a 4. So what I do is I go halfway from my first point to the big point labeled 2, 3, and 4. I'll mark that new point. That's my new point. I roll the die. This time it comes up with a 5, so I go
Okay, we
halfway
get the
from
idea.
my
And you
new
do that
point.
thousands of times, and you get...
an enormous mess of dots. But that's not what...
Here you go. Here's what you get. Be ready for the mystery. And now, look, that's a fractal, and we're making an artificial fractal.
Complex and ordered geometrical structure.
See, they're the same.
The revolutionary idea that a chaotic process can give rise to order is destroying old definitions of chaos
Yes.
clung to for centuries.
Anyway.